Okay, let's unpack this. Today, we are strapping on the regulatory scuba gear and plunging into the surprisingly complex world of liquefied natural gas, or LNG, regulation at sea.
It's a really dense topic, but the sources you've seen reveal some pretty deep friction in global maritime law.
Friction that's actually slowing down innovation in clean shipping, which is why we're doing this deep dive.
Exactly.
So our mission today is to decode the confusion caused by the International Maritime Organization, the IMO. They've set up two huge parallel sets of rules for handling the exact same substance.
And that's the key. It's the same substance.
We need to understand the structural differences between them and really get into why one is generally considered so much stricter than the other.
Right, so you have two main codes running at the same time. The IGC Code, which is the International Gas Carrier Code, and then the IGF Code, the International Gas Fuel Code.
Okay, so break that down for us. What's the real world difference?
The easiest way to think about it is context. The IGC Code is for ships that carry LNG as bulk cargo. So, think of those enormous specialized tankers crossing the ocean.
Got it. The big haulers. And the IGF Code.
That code is for any other vessel, a container ship, a car carrier, a ferry, that's using LNG as fuel for its own engines.
So it's about whether the LNG is cargo for sale or fuel for the ship itself.
Precisely. For the ship's own consumption, not for delivery.
And here's the paradox that just jumps out from the source material. They are both dealing with the same super chilled, highly volatile gas, yet the IGF code, the one for fuel, generally imposes a much higher, much more conservative level of safety requirements.
It's completely counterintuitive, isn't it? Why would the rules for the little fuel system be tougher than the rules for the massive cargo system?
It makes no sense on the surface.
The analogy that helps here is to think about experience versus novelty. The IGC code, that's like the rule book for a professional freight truck. They've been doing this safely for decades.
The rules are mature, they're risk assessed based on years of successful operation.
Exactly. But the IGF code is different. It's like the rules written for a brand new prototype technology, say a hydrogen-powered passenger car.
Okay, so because using LNG as a fuel is newer and integrated into all sorts of different ships.
The regulators got extremely conservative. They were hypersensitive to every single potential point of failure within the ship's own engine system.
That framing really helps. It's less about the LNG itself and more about where it is on the ship.
And how it's being used.
Right. Let's jump into the most contentious area for ship designers, the machinery space. The engine room. This is where the codes just immediately start to clash.
They do, because the engine room is the most restricted space on board, so managing a potential gas leak is absolutely critical.
And the IGF code for the fuel ships,
Right.
It actually allows for two different ways to think about this.
Yes, two core concepts, and that's where the complexity starts. The first, and you could say the safest, is the gas-safe machinery space.
Safe. Sounds straightforward.
It is. It mandates absolute physical prevention of any gas getting into the engine room. So you're talking about robust protections, like mandatory double-walled piping systems.
And here's the first major split. The IGC code for the big cargo tankers, that's the only concept it accepts.
That's right. The IGC demands the highest level of physical containment, period. The confusion comes in because the IGF code offers an alternative.
Which is the ESD-protected machinery space.
Exactly.
Okay, so if it's not gas safe, how does it manage the risk?
Well, in an ESD-protected space, a gas leak is technically allowed to be released into the machinery space itself.
That sounds risky.
It is, but the safety shifts entirely to automated systems. ESD stands for Emergency Shutdown. The whole design relies on sensors detecting a leak instantly and automatically isolating everything.
Shutting down fuel supply, ventilation, everything.
Right. The idea is to contain the event with automation, sometimes while a segregated second engine room keeps the ship moving.
So wait, if the IGC code only accepts the physically safer gas-safe concept, why did regulators even allow this ESD option for fuel ships? What was the thinking?
It really came down to flexibility and cost. Building a truly double-walled, gas-safe engine room is incredibly complex and expensive.
Especially if you're retrofitting an older ship.
Exactly.
Yeah.
The ESD-protected space offered a theoretically cheaper, more adaptable solution that relied on modern sensors and automation. But, many experts argue that relying on automation after a leak has already happened is inherently riskier than just preventing the leak in the first place.
That's why IGC rejects it. It's a fascinating tension, physical engineering versus automated reaction. But then the regulators put this huge technical restriction on that ESD space.
They did. They essentially kneecapped the technology it was trying to enable.
You're talking about the pressure limit?
The strict pressure limit. For any engine operating inside that ESD-protected machinery space, the IGF code strictly limits the gas fuel supply pressure to just 10 bar.
10 bar. And that doesn't sound like much until you realize what kind of engines are needed to move the world's biggest ships. What's the real-world consequence of that 10 bar limit?
It's a massive commercial and engineering roadblock.
Mm-hmm.
That 10 bar threshold technically restricts the use of all the large, high-powered two-stroke gas engines.
And those are the workhorses of global trade, right? The engines on the giant container ships and oil tankers.
They are. And they need much higher pressure for direct injection to get peak efficiency and power. Specifically, engines like the Menam EGI series.
Which are very common.
Very. They operate at fuel gas pressures up to 300 bar.
300 bar versus a limit of 10. That's not even in the same ballpark.
It's staggering. So think about it. If a major shipping line wants to retrofit an existing container vessel to run on LNG, they would probably choose the ESD design because it's simpler to integrate.
But because of that rule,
they're blocked from using the most efficient, high-pressure engine for the job. It forces them towards less efficient engines, or they have to go with the far more complex and expensive gas-safe design.
it sounds like a regulation that is actively preventing engineers from using the best available technology.
That is regulatory dissonance personified, yes.
Okay, let's move from the engine room to the storage tanks themselves. These are often identical tanks, right? But the rules treat them completely differently.
It all starts with how they categorize the hazard level. The IGC Code, for cargo, treats LNG as a Type 2G substance.
But the IGF Code, for fuel,
It treats the exact same gas as the absolute most hazardous category, a Type 1G substance.
and what does that classification actually mean for the engineers designing the ship?
Type 1G implies maximum segregation. It means the IGF Code mandates significantly stricter safety distances.
So the fuel tank has to be further away from the ship's side and bottom than a cargo tank would.
Exactly. Even if the tanks are physically identical, the fuel tank has to be buried deeper inside the ship's structure, taking up more protected space.
Which means less space for cargo. Another commercial friction point.
You got it?
Now, this is where it gets really interesting on the design side. The piping. Both codes agree that if a pipe is super cold, below minus 110 Celsius, it needs a stress analysis.
Correct, because the cold makes the metal brittle. But the IGF Code adds a second, really critical requirement based on pressure.
And this is a huge divergence.
A huge one. It underscores just how conservative the IGF Code is. It mandates a unique stress analysis for any piping system with a working pressure of 1.0 MPa or higher.
And 1.0 MPa is, for context, roughly 10 bar.
Right. So this means those high-pressure fuel lines we just talked about, the ones going to the engine, they have to undergo this incredibly rigorous stress analysis. The same physical pipe on an LNG carrier under the IGC Code might not need that analysis if it isn't cryogenic.
It really feels like the IGF Code is just layering caution on top of caution.
That's the pattern. They're trying to mitigate risks specific to high-pressure gas inside the hull near machinery, and crew risks the IGC, which is focused on those big segregated cargo tanks, just hasn't emphasized as much.
Let's talk about the pipes on the tanks. The IGC Code says cargo pipes have to be fitted above the liquid level to prevent siphoning.
That's the standard.
Yeah.
But the IGF Code actually allows for connections below the liquid level on some fuel tanks.
But there has to be a catch, right?
Oh, a big one. It's only allowed if the entire connection is housed inside a dedicated, pressure-resistant containment area. They call it a cold box. It's designed to ensure that if there's a failure, the leak is completely contained right there.
Okay, let's shift from the hardware to operations. Gas detection and transfer procedures. This is another area where the IGF Code really clamps down.
The difference in sensitivity is pretty striking. Just look at the gas detection alarms. First, we need to define LEL.
Lower explosion limit.
Right. The minimum concentration of gas in the air to potentially ignite. The threshold is much tighter in the IGF Code. It sets the alarm at 20% of that limit.
And the IGC Code for cargo.
That allows a higher limit of 30% LEL.
20% versus 30. That's a 50% difference in the safety margin. It's like setting your home smoke detector to be way more sensitive for something inside the house than for the same thing sitting in the driveway.
That's a good way to put it. And again, it comes down to location and history. A leak in a cargo area is often open to the air. A leak in a fuel system could be right next to a hot engine.
And it's not just the alarm level, it's about where you put the detectors.
Right. The IGF Code demands proof. It requires a specialized gas dispersal analysis or even a physical smoke test to prove you've put the detectors in the optimal spots.
A requirement that's totally absent from the IGC code?
Completely absent.
Okay, what about moving the LNG? Loading it as cargo versus bunkering it as fuel?
Two big points stand out at the connection manifolds: vapor return lines and firefighting.
So, vapor return.
For the big LNG carriers under IGC, those lines, which vent displaced gas safely, are mandatory.
And for the fuel ships under IGF?
They're optional.
That seems to go against the trend of stricter for fuel.
It does, but it's a pragmatic difference. Bunkering is a smaller, quicker operation. But then you look at firefighting, and the higher standards come right back.
How so?
The IGC code requires dry powder monitors at the cargo area. The IGF code demands a much higher standard: a permanently installed dry chemical powder system, plus more portable extinguishers, all ready to go instantly at the fuel connection.
And finally, there's a unique time constraint in the IGF code, something about a 15-day rule.
That's the mandate on fuel stability. It requires that the tank pressure and temperature must be maintained for a minimum of 15 days after any safety system activation or after bunkering.
Why 15 days? That seems so specific.
It's there to mitigate risks like stratification, which is a big deal during bunkering. That's when you get layers of different temperature LNG, which can lead to rapid, unpredictable pressure spikes. Requiring a long period of stability management ensures the ship stays safe, even if it loses power to its gas systems.
So when you add all of this up engine rooms, tank distances, pipe analysis, detection, the overwhelming finding is that the IGF code has a much higher safety bar.
Often drastically stricter, even when the systems are functionally identical.
What does that actually mean for the people building and operating these ships?
The practical impact is huge. It's introducing unnecessary friction and, honestly, potential safety gaps. Shipyards, classification societies, they all have to apply different, sometimes conflicting rules to the exact same equipment.
Which increases the chance of mistakes.
It increases the potential for misinterpretation and compliance errors. If the goal is safe adoption of LNG fuel, this is completely counterproductive.
The sources we looked at are pretty clear on this. They say the IMO needs to take proactive action to harmonize these codes.
Especially around the machinery spaces and the piping analysis, they need to be reviewed and updated based on current risk assessment, not just what's historically been done in the cargo sector.
Because at the end of the day, if there is no technical reason for having two different safety standards for the same piece of gear,
then the most stringent standard, the one with the greater safety margin, should logically apply to both. The current split just creates ambiguity where you need certainty.
And that leads to our final provocative thought for you to chew on. Given that LNG carriers have a long, successful safety record under the IGC code, why is the safety margin so much higher when that exact same LNG is used as fuel? Does this regulatory split tell us that maritime safety bodies view the risk to a high-value, temporary cargo differently than they view the fundamental risk to the ship's own propulsion, its crew, and its ability to operate safely? It really makes you consider the immense challenge facing these international bodies as they try to keep pace with the necessary global shift to cleaner fuels.